Section 4.5 in college algebra is referring to solving different types of exponential and logarithmic equations. Now back in section, I think it was 4.1, we discussed solving exponential equations that had a common or a similar base that we could rewrite as a common base. But today's lesson will have other types of problems, exponential and logarithmic. So first, get my cursor going. Number 1 is 10 to the negative x power equals 0.0347. Well, the variable is trapped up in the exponent, and the only way we can bring it down is by applying a logarithm. Now, if I want to use my calculator, I always tend to ignore the change of base rules, and instead I either use a common log or a natural logarithm. It ends up being the same work, I just always do it this way. So a common logarithm is base 10. It would be very wise of me to apply a common logarithm to both sides in this problem, because the common log and the 10 will cancel each other out, leaving me with negative x equals, and then I will just have to type in log of 0.0347. Because these are numbers, they're just not nice numbers. So negative 1, and I don't know where they sit around, but negative 1.46, and then if I divide both sides by negative 1, I get positive 1.46. The next question is again a base 10 exponential problem, so if I was to choose a logarithm of my liking, I would choose a common log, because the common log will cancel with the base 10, leaving me with the 3x plus 1 now down out of the exponent. And then log of 92, I just need to type. And I get 1.96. Then I'm going to subtract 1 to solve the linear equation and divide by 3. So I get 0.321. On number 3, I have a base e, so a natural logarithm would be very wise of me, because natural log and base e will cancel each other out. So the natural log of 3.65 is 1.29. Let's see, get this out of my way. Next set of problems. These are still exponential problems, but you're going to notice their bases are not 10s nor e's, so it's not going to matter which type of logarithm I apply. I tend to use natural logarithms simply because it's one less letter and I'm lazy. So when you apply a logarithm, the whole point of that is to bring the exponent down in front. So I have x times the natural log of 5, which is just some gross decimal, equals the natural log of 18. So if you think about what we have here, x times a number equals a number. To solve for x, I would divide by the natural log of 5. And this is something I would type on my calculator. So natural log of 18, make sure you close your parenthesis after that first logarithm. And divide by natural log of 5, I'm going to just type on my personal calculator. And I get 1.80 when I round. Number 5, exponential problem. They do both have options to rewrite as different bases, but neither of their bases are common to each other. So I'm just going to have to apply a logarithm. So again, I like natural logarithm, but you can do whatever you want as long as you do the same to both sides. The exponent will come down in front. So I have the quantity 2x plus 3 times whatever the natural log of 4 is equals the natural log of 9. So again, natural log of 4 and natural log of 9 are just values, numbers. So if I divide by the natural log of 4 on both sides of my equation, that's something I'm going to have to type in. And I get still 2x plus 3 on the left side equals 1.58. I'm going to subtract 3 and then divide that answer by 2. And I get an answer for x of negative 0.708, but I think I rounded to the hundredth, so I should say negative 0.71. I tend to keep all my decimals on my calculator as I type. I don't round off into the end, so sometimes my work and my calculator doesn't exactly match, but as long as you're within a tenth, we're good. Number 6, again, don't have any common bases, so I'm just going to apply whatever logarithm I want, common or natural. Just for variety today, I'll do a common. In this case, both the exponents will come down in front of their logarithms. So I've got 4x minus 1 times whatever the log of 3 is equals x times whatever the log of 2 is. Now this is a special case because I've got variables on both sides. So I'm going to go ahead and distribute whatever the log of 3 is, and I'm going to change log of 2 to a decimal as well. So log of 3, here I will have to round off a little bit. So what I have is 4x minus 1, and we're going to multiply him by the 0.477. So we're going to distribute him in, And then log of 2, and again I did common log this time, is 0.301x. So trying to solve this equation, 4 times 0.477x gives me 1.908x, and then distribute that to the -1, I get 0.477. And then it's gross, but it's a linear equation, and I'm going to subtract 0.301x from the right side and get 1.607x. I'm going to add the 0.477 over, and then of course I'm going to divide by 1.607. So these are less exciting. Whoa, that's a 7. Because I do have to round off quite a bit. There are ways to keep the entire decimal in your calculator, but I'm not a careful enough typer to do that. So my answer I get is 0.297, and I don't remember if they told us where to round, so of course it would be different if they told me the tenths place or 100,000ths or something. Number 7, same process. Choose your favorite logarithm. I'm going to choose, actually I'm going to skip 7 for the sake of time. Move on. Number 8. The base is not isolated, and you want to isolate the base before you begin applying logarithms. So I'm going to go ahead and do that, and I'm going to just, since I know I'm going to have a decimal, I'm just going to type it in and get 0.246 equals e to the negative 0.12x. So since my base is an e, a natural logarithm would be very wise. The natural log and e will cancel, and then the natural log of 0.246 is something. I'm going to type that in. It's a negative 1.402, and the natural log and e will cancel, so we have a negative 0.12x. To solve for x, I'm going to divide by the coefficient of negative 0.12, and I get approximately 11.687. Rounding off, as long as you're close, we're good. Okay, no common bases here in number 9. I'm going to have to apply a logarithm. I go back to my old favorite natural logarithm. Nothing will cancel. The only thing that will happen is this exponent will come down in front. So we have the natural log of 35, some gross number, equals the natural log of 7. I'm going to solve by dividing over the natural log of 35 on my calculator. So natural log of 7 divided by natural log of 35. And I get 1 minus 2x equals 0.547. I'm going to subtract 1. We get negative 2x equals negative 0.453. And I did round off there, so I'm not rounding off on my calculator. Might be a little dangerous, so your answer might be slightly different, but I got approximately 0.226. Okay. When you are solving a problem with logarithms, a couple rules. First of all, you do not want more than one logarithm in the problem. So if there is more than one logarithm, you have to do some clever rearranging or possibly condensing. And once I have it where it's set up that there's just one logarithm on each side of the problem, then I want to exponentiate. So here, log of 5, common log of 5 plus common log of x, if I bring that together using my exponent properties, I have the common log of 5 times x, or 5x, equals 2. Now remember, we're exponentiating, and he's secretly a base 10. So what I'm going to exponentiate with is a base of 10. So 10 to the common log will cancel, leaving me with 5x, and then 10 squared is 100. So divide by 5 on both sides, and you get 20. Now you do need to think about extraneous solutions in this case. And I know for a logarithm, I cannot take a logarithm of anything 0 or smaller. So if my answer came out negative, and when I put it into the logarithm, it gave me a log of a negative number, that would be an extraneous solution. We will see examples of that, especially when we have quadratics. So bringing these logs together, if I multiply x times x minus 3, I get x squared minus 3x equals 1. I have a common base of 10 here, so exponentiate with a 10. X squared minus 3x, and then 10 to the first, of course, is 10, and this is definitely a quadratic that I'm going to solve by factoring. I get x minus 5x plus 2 for my factors. So supposedly I have two answers, x equals 5 and x equals negative 2. However, if I go back up to this logarithm, for instance, if I put a negative 2 into that logarithm, that would be log of negative 2. That's going to be an extraneous solution. 5 will work, however, so he is a solution. Number 12, we're going to bring these logs together through the quotient property. So common log, base 10, and then x plus 1 in my numerator, x minus 1 in the denominator. We're going to now exponentiate with our base of 10, which cancels the logarithm. So x plus 1 over x minus 1 equals 10, or 10 over 1, since I see I'm going to have to cross multiply this proportion. 10x minus 10 equals x plus 1. Subtract x, 9x equals 11. X is 11 ninths. Generally, when you get a quadratic, is most of the only times you will see extraneous solutions. That was not a quadratic, but I checked quickly that it would work. Now here, we're going to bring these logarithms together and these logarithms together, and we definitely need to watch out for extraneous solutions. So that would be x over 5. And then here, we have log of 2 divided by x minus 3. Now, exponentiating with a 10 on both sides is kind of exciting because it's going to cancel both logarithms and leave you with a neat little proportion to solve. And this proportion will produce a quadratic. So cross-multiplying, I'm going to get x squared minus 3x equals 10. This is the same quadratic we just had the other minute. So x minus 5, x plus 2, x equals 5, that answer will work fine. X equals negative 2 will not work, however, and one particular place I see it won't work is right there. Can't take a log of a negative 2. Here, we only have to condense this side together. So, using the quotient property, 2x minus 1 over x minus 2. I would exponentiate both sides with an e, kind of neat because the e in natural log will cancel, leaving me with x over, or equals 2x minus 1 over x minus 2. Now this is a proportion. You want to cross multiply it, and then once again we get a quadratic. I'm going to subtract 2x and add 1, so we get x squared minus 4x plus 1 equals 0. Now, they only want real answers in this chapter, and I'm going to quickly calculate the discriminant. Remember, the discriminant is b squared minus 4ac, and if this comes out to giving me imaginary answers, I'm not going to bother continuing. So b squared is 16 minus 4 times 1 times 1. Now, kind of bad news. The discriminant is positive, which means I will get answers. Double bad news, it's not factorable, so you've got to use one of your favorite methods for solving this. I already kind of halfway did quadratic formula, so I'm just going to continue with quadratic formula. Negative b plus or minus, I see that the discriminant will be a 12 for 2a. So 4 plus and minus 2, square root of 3 over 2, still no good. Divide everybody by a 2. 2 plus or minus square root of 3. Now, if you typed 2, I'm not worried about the plus, but 2 minus square root of 3. Oh, if I can type. 2 minus square root of 3 is 0.268 roughly. The reason I bring that up, 2 plus square root of 3, I should also type in, is 3.73. If I go back to this particular logarithm, now neither one of those are negative, but when I were to substitute in 0.268 into this logarithm, I would end up taking the natural log of something negative, which I know cannot happen. So this is going to be an extraneous solution, so this decimal is the only acceptable solution, and 2 plus square root of 3 was the official answer, but I would accept the decimal version of that. And then on 15, I don't like logarithms on both sides unless I can group them together, so what I'm going to do is I'm actually going to add this logarithm to the other side, and then I'm going to condense my logarithmic expressions. So condensing these guys down to a multiplication problem, ew, it's FOIL, 2x squared plus x minus 2x, so minus x minus 1 equals 1, and then this is a base 10 logarithm, so I'm going to exponentiate with a 10. That's going to leave me with 2x squared minus x minus 1 equals 10. And then, of course, subtract 10. And, of course, it's not factorable. So, negative b plus or minus square root of b squared minus 4 times a times c all over 2a. So simplifying that, I'm going to get 1 plus or minus, looks like this is Oh goodness. 8, 44, 88, 1, oh, I think I lost a negative. That's a negative 11. So it's 1 plus 88, which is square root of 89, over 4. Now, I'm not worried about the positive answer, but if I were to calculate 1 minus the square root of 89 and divide it by 4, I get a negative 2.108. And I think right here we're going to have issues. If I did 1 plus square root of 89 over 4, I get 2.608. So I think the green answer is fine, but the red answer is going to be extraneous. Whoops. So always check for extraneous solutions. And then one application I think we can squeeze in for time, page 372. I'm sure it's a good one. 372, number 67, compound interest. So how many years to the nearest year will it take for money to double if it's invested at 15% compounded annually? So first of all, the compounded annually formula is this guy. And I always put the NT in parentheses. And they don't tell you how much money you're going to double, and it's because it doesn't matter. If you put $100 into the bank, you're going to have $200 when you're done. And if you think about how you would solve that equation, you would end up dividing it over. So I don't care what the numbers were, the ratio would always come out to a 2 and a 1 because of the doubling aspect. So I'm just going to put 2, and you can put a 1 here if you want, but I'm just going to leave it off. The rate was 15%, so 0.15. Compounded annually means once. And then up in the exponent, it's 1 times t, or just t. And I don't know t, I need to solve for it. So of course I can simplify this. 2 equals 1.15 to the t power. I'm going to apply my favorite logarithm, the natural logarithm. So I have the natural log of 2 equals t times the natural log of 1.15. And I'm going to divide both sides by the natural log of 1.15. And these don't always come out pretty. In fact, they hardly ever come out pretty. So we're going to give ourselves a time window, basically. Now watch out on these problems, because oftentimes you'll solve for t, and that represents how many years have gone by. But they'll want to know exactly in what year. So if the problem happens to say, time starts in 1996, make sure you go back and add it. But I got approximately 5 years. That's how long it'll take for the money to double. Okay? And that's all we have time for, and that's good, because we're done.